Okay, so in this particular lecture, we will be talking about the topic permeability. Now, so what does the word permeability means? So permeability can be defined as ease with which a fluid can flow. Okay. In other words, also we can define permeability as it is the ability of a material to allow penetration of something through it. Okay, let's understand with an example. For example, there is marble flooring present in your house. Okay, suppose this is your marble flooring. Okay, now if you by chance spill some water on it, okay, you by chance have spilled some water on it, you will see that this water stays for a very longer period of time. Okay, until you wipe it off with a cloth. Okay, it will stay for a very longer period of time. Okay, this water will stay for a very longer period of time. On the other hand, if you have a unpaved surface, okay, let's take the case of soil. For example, you are in the park and you there spilled the same thing, the same water you spilled there. You will see that after 1 or 2 minutes the water will start penetrating into the ground. Okay, the water will start percolating into the ground, and it will vanish off after 1 or 2 minutes. So why is there a different behavior of water in the two cases? Because of the permeability of the material. In the first case, which was of our marble flooring, the marble flooring had a very low permeability. Okay, the marble flooring was having a very low permeability, and that is why the water was not able to percolate in the underlying layers. On the other hand, in our second case, our unpaved surface, or you can say soil was having high permeability. Okay, high permeability, and therefore the water was able to penetrate into the sublayers easily. Okay, so that's the idea about permeability. So let's just again work out on our primary definition. So permeability, in general term, permeability is defined as the ease with which a fluid, okay, a fluid can flow through a porous media. Okay, porous media. Now, since we are dealing with soil mechanics, so this fluid, which is a general fluid, can be any fluid such as water, okay, oil, okay, or any gas. But since we are dealing with the soil mechanics, the fluid we consider is water only. Okay, and the porous media is also in general term. Since our discussion is limited to the soil mechanics, so our porous media will be soil. Okay, porous media is nothing but any medium which has pores in it. Okay, any medium which has pores or voids. Okay, pores or voids in it is called a porous media or porous medium. Okay, now let's just talk about a pipe flow a little bit. Okay, so in fluid mechanics or hydraulics, we all have studied flow through pipes. Okay, suppose this is your pipe boundary. Okay, I'm only consider a section of pipe. Okay, this is your pipe boundary. Okay, and suppose it is having a fluid, let's say water. Okay, and the water is flowing in this direction. Okay, Let's name it this section as A and this section as B. Okay. Now fluids always flow. We know that fluid flow takes place from high head. Okay. High head to low head. Okay. High head to low head. Okay. Now what is this term head? What is this term head? So head can be seen as a term which represents energy. Term which represents energy possessed by a fluid at a specific point. Okay. So energy represented by a fluid at a specific point is represented in terms of head. For example, you must have studied about piezometer. Now if I insert two piezometers here, okay, if I insert two piezometers over here, let's say at the first point or the first section A and the okay and the second section B, this one is the second section. Okay, now what will happen? The water will start rising in this pipes, in this stand pipes, or you can say the piezometer, and will rise up to corresponding to its energy only. Okay, for example, in the pipe A, the water has rised till here. Okay, point 1, and in the piezometer B or the standby B, the water will rise to a point slightly or somewhat lower than the point at which it has raised in the section A. Suppose in the section number B, the water level is at 2. So you can clearly see that there is a head difference. Okay, there is a head difference that is occurring between the two sections. Okay, there is a head difference. This is the head difference. Okay, this is the delta H. Okay, or you can say the head difference. Okay, why this head difference is occurring, or why there is a loss of energy in the direction of flow? The loss is mainly because of the frictional forces that are acting on the boundary of the pipe. Okay, inner boundaries of the pipe. These frictional forces are acting between the interface of the inner boundaries of the pipe and the interface of the liquid surface. So that is why as we are approaching towards right direction, the pressure, or you can say the energy is decreasing. Okay, let's proceed further. Now if I talk about head, there are generally three types of head. Okay, the first one is datum head, the second one is pressure head, the third one is kinetic head. This one we also call it as velocity head. Okay, so these are the three types of heads. These are nothing but these represent the three types of energy possessed by any flowing liquid. The first one will be the potential energy. Okay, the first one is the potential energy. Okay, the second one is the pressure energy. Okay, the second one is the pressure energy, and the third one is the kinetic energy. Okay, and the third one is the kinetic energy. Now if we sum up the datum head and the pressure head, if we sum up the datum head and the pressure head, we combinedly call it as piezometric head. Piezometric head. Okay, so the datum head and the pressure head combinedly is called the piezometric head, or you can say that piezometric head is nothing but the pressure head plus datum head. Okay, so let's understand these heads in a better way by taking an example. Okay, let's take case of a pipe only. Suppose this is my pipe section. Okay, now my fluid is flowing in this thing, and the direction of flow is from left to right only. Okay, now what I do is I install multiple piezometers at intermediate points. Okay, these are the multiple piezometers, or you can say what I've done is I've connected a simple vertical pipe at multiple points. Okay, let's say this is the point number 1, this is point number 2, 3, 4, 5, 6. Okay, now what will happen? Water will start rising in this thing. Okay, water will start rising in this thing, of course. If I connect all these points, okay, if I connect all the piezometric heads, all, you can say that all the points that represents the pressure head plus datum head, then this line is called the HGL, or hydraulic gradient line. Okay, hydraulic gradient line, HGL, or this also represents the piezometric surface. Okay, piezometric surface, since it is the locus of all the piezometric points, so therefore it is representing a piezometric surface. Okay, this piezometric height, or you can say this total H, is nothing but the datum head. Okay, DH, datum head plus pressure head. Okay, the datum head plus pressure head. Datum is nothing but a reference, you can say a reference or a benchmark type of a thing from where we measure all of our heights. Okay, you can consider it to consider datum as a zero level point. Okay, so all the heights will be measured from our datum only. Okay, for example, if this is our datum, so all the heights will be measured from this point only. Okay, so this thing represents the piezometric head. Okay, piezometric head, that is nothing but the pressure head plus datum head. Okay, pressure head is P by rho g. Okay, this pressure head is P by rho g, and the datum head is nothing but the height. Okay, from our reference point. Okay, this thing. Okay, this elevation is our datum head. Okay, for example, it is Z. Okay, so our piezometric head will become P by rho g plus Z. This is the piezometric head, and to this head, if I add the kinetic head also, V square by 2g, what will happen? This point will shift upwards. Okay, for example up till here. Okay, and similarly for all the subsequent points. Okay, and if I now join the total headline, okay, or you can say that the locus of all the total heads at different points represents the total energy line. Okay, it is nothing but the summation of pressure head P by rho g, datum head Z, and the velocity head V square by 2g. I hope this thing is clear. Now let's proceed further. Now if I give you two cases, okay, suppose these are the vertical pipes. Okay, this is case number 1, this is case number 2. What you are doing is you are pouring water from the top. Okay, you are pouring water from the top. The difference in the two cases here is the first one is having soil sample in between. Okay, this is our soil sample. Okay, this is our soil sample filled in between. Okay, let's say up to thickness T. Okay, or height T. Okay, and this one contains no soil sample. So if I ask you in which of the two following case, okay, I will be obtaining water from the outlet earlier. Okay, of course you will say the second case because there is no obstruction. Okay, you can say there is no obstruction to the flow. Okay, but in the first case there is a obstruction present to the flow. Okay, now let's analyze what will be the effects of introducing our soil sample in between our free flow. Okay, so this is our soil sample. Okay, let's say our soil sample is present in dry state. Okay, dry state, that means our soil sample will be present in two-phase system. Okay, there will be two materials only, the soil solids and the in the voids air will be present. Okay, so now what I do is I just put this soil sample in a glass tube, or you can say a hollow tube. Okay, so what I have done is I have just made my soil sample fit into a glass tube. Okay, now I provide the inflow of water, okay, from the left surface. Okay, so what will happen, the water will start filling this tube. Okay, now what will happen, that the water molecules will start percolating into or start permeating into my soil sample. Okay, it will be penetrating into my soil sample. Okay, so what will happen, the flow path that was initially straight, okay, and was free of any obstruction will have to face some obstruction, and the flow path will become tortuous. Okay, tortuous in nature, or you can say zigzag in nature. Okay, where the fluid particle will find the space, it will bend accordingly along the free surfaces available and exit the soil sample. Okay, so what is happening here is, you can say that velocity are changing in this region. Okay, in my soil region, because soil is an obstruction to the flow, and accordingly parameters of the flow will start changing because of this obstruction. Okay, now we know that from our basic knowledge of fluid mechanics that discharge is equals to area into velocity, and also we know that according to equation of continuity, this discharge is always constant, okay, throughout the section, that is A1 V1 is equals to A2 V2. For example, the cross section area of this pipe is A. Okay, now what will happen? I can apply this equation of continuity at any two locations. For example, let's say this is my section 1 1, this is 1 1, and this is 2 2. Okay, now if I apply the continuity equation, I will be having A1, area at section 1 and velocity at section 1 is equals to area at section 2 is equals to velocity at section 2. Okay, so this area will be nothing but A only. Okay, and let's say this V is nothing but the discharge velocity. Okay, and this area A2 will be the area of this soil sample. Okay, let's say this is the area. Okay, area of this soil sample. Okay, so area of soil sample, okay, into velocity of fluid through soil sample. So velocity through soil sample.